This week we'll be looking at Chapter 15, Mineral Resources and the Environment, and this topic may have been what you imagined this whole course was going to be about. Here we're going to be looking at the impact of mining at Earth's surface and how it affects the environment. I also wanted to give you a heads up that the quiz this week will also focus on Chapter 15, and I'll be bringing in some of my professional experiences. I have some experience in this area, so there will be a little bit of material that goes just a bit beyond the chapter content, and wanted to give you a heads up on that. More on this later when I talk about specific mining methods. We'll start this chapter by looking at one of the case histories that your book points out. It's now a golf course near Golden, Colorado, and it was once a mine, an open pit quarry for over 100 years where clays were extracted from between limestone beds and all the material mined out, where the clay was used in order to manufacture bricks. These bricks were used as a basic building material for a number of buildings in the Denver area, including Colorado's governor's mansion. After laying dormant for some years, it was later transformed into Fossil Trace Golf Club and is now used for a very different purpose today. I wanted to point out that this is a unique example of mine reclamation, and it's not like we can go out and take all the old mines and transform them into golf courses and solve the problem of mine reclamation. Stands as a unique example, but is a good example of how repurposing a land or finding a new use for land often helps solve problems, or can sometimes solve problems of mine reclamation. Minerals can be seen as the backbone of modern societies. The availability of mineral resources can be seen to some extent as a measure of the wealth of a society. Another way to say that is that if you have an economy that is deprived of certain or needed or essential mineral resources, you can constrain the growth of that economy. And that's certainly true. Mineral resources are important in everybody's daily life and in our overall economy, in the economy of most nations. In our daily lives, we couldn't set an alarm to wake up in the morning. We couldn't get to work. We couldn't turn on a light. We couldn't get dressed without relying on resources that we extract from the earth. Mineral Processed minerals and materials account for 5% of the United States gross domestic product currently. It has been higher in past years, and in other nations it represents a much more significant or a much less important part of the economy. One of the important things to recognize about mineral resources is that they are non-renewable. If we have a certain amount of chromium available to us, once we use up all that chromium, you can't manufacture more. You can go back and recycle the chromium that had been used in the past and reuse it. You can go back to chromium ores that once we couldn't economically obtain chromium from and try again to get more chromium from them. So there are certain things that we can do, but once all of a certain element is used up, there's no replenishing the supply on Earth's surface. When I talk about how minerals and mineral resources are part of everything that we use in our lives, we can look, for example, at all the components of a modern office and see the dependence on those components on mineral resources. So your textbook does this with this figure where it shows you, for things that you might find in a typical office, what type of mineral resources were required in order to produce those products. This is, well, it's no longer in your textbook, but I'm going to provide an extra resource that's a government data sheet showing for different types of mineral resources how much of the United States need in that area comes from imported sources and how much do we produce locally. One thing I'd like to point out is that the number one mined product in the United States is not anything that you'd think of on this list. not something that would probably come to mind, but the number one mined product in the United States is sand and gravel. We need it for so many purposes in everyday life. For pavement, for example, we need sand and gravel. We need sand to manufacture glass. And so sand and gravel is considered a mined commodity and usually considered the number one mined commodity. For a number of materials, and you can see from this list things like asbestos and bauxite, we get almost all of those resources from outside the United States. Uh, and the it some have argued that the United States economy is critically dependent on foreign sources of some key materials, such as rare earth minerals, which come largely from China. And our relationship with China is influenced by how we rely on them for those sources. So I'll pick some of them like thorium and yttrium on this list that come from sources outside the United States and where our dependence on other nations to continue to supply us with products that we need in order for our growth depends on our relationships with those countries. When looking at various metal ores, one of the things we consider is what's its concentration in Earth's crusts, what the concentration needed in order to constitute an economically feasible ore body. That is shown in the third column. What is the percentage of that element in an ore? And then by taking the ratio, we'll get the approximate concentration factor. So consider each of the metal elements shown on the left. You'll see that something like gold is not very common in Earth's crust. But fortunately, we don't need to have a lot of gold in order to constitute an ore, so we only need a concentration of a factor of about 2,500, which makes finding a gold deposit a fairly rare thing, but not as rare as a mercury deposit, which you'll see needs a concentration well beyond its natural concentration in Earth's crust in order to constitute an ore. Something like iron is fairly abundant in Earth's crust. You'll see that it constitutes 5% of Earth's crust, but we need it to get up to 25 or even close to 70% in order to constitute an ore body. And so we need a concentration factor of somewhere between 4 and 14%. Iron ores aren't that rare. We have plenty in most continents, and we mine that in a lot of different locations. Whereas something like mercury, which needs such a high concentration factor, it's going to turn out those are much more rare. Now let's consider what constitutes a mineral resource and what constitutes a mineral reserve. A mineral resource is a usable economic commodity that can be extracted from naturally formed materials, whether compounds, elements, minerals, or rocks. Whereas a mineral reserve is the portion of a resource that is identified and currently available to be extracted legally and in an economically feasible way. So the things that define or determine what's going to constitute a mineral resource and what's going to constitute a mineral reserve include the factors that are geologic, technical, economic, and legal factors. Geologic factors, those are going to help define what has sufficient concentration in order to make the element sufficiently abundant. Technological constraints are we need to have a mining method that's going to be appropriate for the ore body, and we need to have a mineral processing process that's going to be allowing us to extract what we need from the ore. What are the economic factors that constrain these things? What's the current commodity price? Is the price of gold high? Is the price of gold low? That would constitute whether or not it's worth beginning or closing down a mining project. And legal factors, if you have an ore body that's in a national park and the national park doesn't permit any mining of the resources inside the boundaries, then it's off limits and it couldn't possibly be considered a reserve. While it still may be a mineral reserve, which, with a change of the law, would allow the resource to become a reserve. These topics are described in figure 15.2, where the distinction between reserves and resources are identified. So you can have across the top both identified and undiscovered resources. You could also have, looking vertically, economic, marginally economic, and sub-economic categories in which to classify resources. So in order to constitute a reserve, you have to have both identified and economically viable or feasible methods of getting at the reserves. Even within reserves, you might have some portions of a mine that they set aside for times when a commodity price is high, in which those become marginal reserves, and you have the continually operating part of a mine and a part of a mine that will only be opened up when the commodity price rises. So that's how these issues are related. The economics, the technological feasibility, the geologic conditions, and also the legal constraints. Mineral resources are non-renewable. We can't manufacture more gold. We have to make do with the amount that we have. Because there is a finite amount of mineral resources and we have growing demands of resources, that sets up internal conflicts within our society and within our economy that we face on a regular basis. In addition, we have a shortage of supply due to growing economic industrialization, with more developed countries consuming a disproportionate share of the mineral resources, which means that our international relationships are going to be affected by our expectation and accustomed use and accustomed access to mineral resources, and new economies or emerging economies wanting to get a share of resources to enable them to thrive and to grow. There is a natural erratic distribution of various mineral resources, and we also have an uneven consumption of the resources. Highly developed countries use the most of our resources, but don't necessarily have an equivalent supply of those resources, which means a well-developed nation like the United States is becoming dependent on nations where natural resources exist, and our international relationships are affected by those. Oil is probably one of the places where we're most aware of this, but mineral resources also affect our international relationships. What are our choices in responding to the limited availability of natural resources? We can find more sources, and we're doing this by trying to find new ore bodies located in different places where we haven't done a lot of exploration. We can find a substitute. So if you can't get access to gold, what might be the reasonable alternatives? We could also recycle, making use of products that have previously been mined and are no longer in use. We could also use less or make more efficient use of what we already have available to us. And finally, our last choice is to do without. But those are our choices. We don't have any other choices on those. And each one of those has both an up and a downside, and we have to learn to live with those. We have lots of different types of mineral resources, and often we describe the different types based on how we use them. We have a number of materials that are used for metal production and technology, and we have a number of construction materials that we use for road construction, building construction, for example. Then we have the agricultural industry, where a significant or a large volume of materials are needed for fertilizers, and those actually have to be mined. We also have mineral resources that are needed for the chemical industry. Often these become very specialized, where a specific type of mineral is not needed in great abundance, but it might be a very rare mineral that we need to find a mine or a source. There are other different kinds, which include precious gems. We also mine materials that are used in cosmetics, in food, in a Hershey's bar, for example. And we also have energy mineral resources that are mined, the most common of which is coal. So these are sort of various types of mineral resources. Let me also introduce an interesting point. What is the most common or abundant or the most commonly mined material? What's our number one commodity for mining? It's sand and gravel. You might not have expected that, but that's our number one product in mining, and it's not something more exciting than that, but it's something that we use every day for road construction, for example. And I think that's useful to keep in mind, because when you think of mines, you might think of something at a great distance, far away, out west or something. But in fact, we're not going to get sand and gravel from out west. If we need sand and gravel for road construction, we're going to find a nearby source. We also need sand for something as simple as glass production. So we're going to need to have lots of mines for sand and gravel so that we don't have to haul those materials a great distance. The geology of various mineral resources is something that we're going to focus on next. And the genesis of some of the common mineral resources are distributed from coming from a number of different processes. We have igneous processes, metamorphic processes, sedimentary, biological, and weathering processes. And different kinds of mineral resources come from different types of these processes. Some examples that we're going to consider, and I'll be depicting these in graphics in a minute, but for now, let's go through the igneous ones. Some examples would include diamonds that are scattered within an igneous kimberlite, or hydrothermal deposits that might lead to gold and silver mines. Metamorphic processes. There are some contact metamorphic processes, such as a very hot magma creating a skarn, or a regional metamorphism where a mountain belt is formed and the pressures that are experienced within a region create something like asbestos that we used to mine in abundance. There are sedimentary processes that create ore bodies, river deposits, which will give us that sand and gravel that we need so much of, evaporite deposits, where water flows into a formerly dry lake bed. That water evaporates, leaving behind some salt or halite and the gypsum that was once dissolved in the water. Also, something known as placer deposits, which come from the bed of a river, and I'll be discussing those in a picture in a moment. There are also biological processes where calcium carbonate would come from critter shells that accumulate in areas and constitute an ore body for calcium carbonate, or calcium phosphate in fish bones might be the basic materials needed to form the mineral known as apatite, and it is abundant in bones, and it can be transformed by biological processes to be concentrated in sufficient quantity to constitute a resource. There are also weathering processes where whatever the rock used to be is weathered by a strong climate to become something different and thereby constitute an ore body. Another way of depicting these is shown in this table, which describes different kinds of processes, some examples of the ores that come from each of those processes, and some sample locations. We have some in the United States, such as Stillwater, Montana, has chromite that came from crystal settling in an igneous process. We also have, under igneous, we also have some pegmatites where beryl, and lithium are mined from the Black Hills of South Dakota. We also have hydrothermal deposits where copper is found in abundance in a location such as Butte, Montana. Skipping down, it's probably not surprising that under biological processes, if we're looking for phosphorus, it came from where the bones of fish have created this phosphorus resource in Florida, where ocean fish that lived in the ocean now have led to this ore body in Florida. In weathering processes, some of the interesting ones are that the residual soil that forms in a number of different tropical or subtropical environments can create a material known as a bauxite, where aluminum is mined in such places as Arkansas to some extent, but more commonly or more abundantly in other places around the world in tropical environments such as Jamaica. When looking at the geology of mineral resources, when we're looking at metallic ores, we look at useful metallic minerals that can be mined for profit. The mining potential depends upon the current technology, the current economics, and the politics, with an emphasis on the profitability, the technological feasibility, and the demands. So again, one interesting thing about a mine is that they'll often have certain portions of their ore body that they don't plan to mine initially, but that they might take advantage of later if there's a change in the commodity price. So even within a mine itself, they might have places where future expansion will depend on new technological or new economic conditions making the mining process feasible. I introduced this before, that the concentration factor is the concentration necessary beyond its natural concentration within Earth's crust in order for it to be in order for profitable mining to occur. For gold, that concentration factor is about 5,000, but it varies for other metals, and it's also variable over time. How is it variable over time? Because if new technologies come up that allow us to get at the metal mineral in in different concentrations where it might not be so abundant, then we can take advantage of those new technological methods. Also, if the commodity price rises over time, then we might not need to have such a high concentration factor in order to constitute an ore body. One of the first types of ore deposits that I wanted to consider is a kimberlite. These are I don't think you can get more dramatic than this. The kimberlites are thought to come from very deep in Earth's mantle, where very violent eruption comes from the deepest location and thrusts itself all the way up to the Earth's surface in an explosive and powerful event. The creation of a kimberlite also has the pressures and temperatures at high enough that they can form something very rare, and that is diamonds. So a small number of diamonds could be created within a kimberlite, and that would allow the kimberlite material itself to be mined. And here you'll see a depiction of what a kimberlite mine might look like in cross section in the top, and then an actual picture at the surface in a panoramic view, so that it has something of a distorted view, so that you can see what's left behind after a kimberlite has been mined, or during the mining process, probably after it was mined, because that much standing water would be difficult thing to mine under. Here's another depiction of a type of an ore body, and here we have a stratified deposit where at the bottom, you see we have a chilled fine-grained material that was once molten, and because it was so hot, then we have a layer of ore chromite that has some magnetite in it, and this actually is stratified because it had come into contact with the hotter material that lay beneath it. Above that, you'll find a different material, the coarse peridotite, that has a few layers of chromite within it, but not with the concentration of the material below it. How this would have formed is probably through contact metamorphism. The very hot material below caused a change in the material that was above it that created this layer in between that actually constitutes the ore. Another type of another type of igneous process is the hydrothermal deposit. These are very large, where you have a huge intrusive igneous rock below that's at a high enough temperature and with volatile contents that it has water and steam and mineral rich waters circulating in the area around it. Because that water is circulating with a concentration of minerals within it, when that water eventually dissipates into the rock or evaporates, it leaves behind the minerals that form in this purple or blue contact metamorphic zone where the mineral deposits might be present. So that's though these are often create some of the largest mining resources that we take advantage of. A very different type of mineral resource would be created in a placer deposit. Placer deposits are heavy minerals that are left behind in some sort of fluvial or river-based process. Sediments are carried along with the water, and where you have a strong current, you probably don't have any of the sediments being deposited. But when the currents change, you might have point bar accumulation or bed load accumulation of the heavy materials at the bottom. You'll see shown in black where a location where some of the heaviest minerals might accumulate, and these would accumulate in areas where the current is slowed down enough to let them come out of suspension in the water, and they'll tend to accumulate in the places where only heavy minerals could come out of the current and fall out. And so where they do, they happen to form a placer deposit. Another very different type of mineral deposit comes from an evaporite. This is a dried lake bed. If rains come along or snow melts up in the mountains, carrying water laden with minerals down into this lake bed, when the water evaporates, it leaves behind whatever salts happen to be in the minerals that were uphill. So this is how you can have an accumulation of evaporitic materials. So salts and gypsum and carbonates might accumulate in such a mineral deposit. These evaporite deposits are not that uncommon in the United States. In fact, they're pretty common. And there are some in Mississippi, Louisiana. These are salts that have accumulated during periods where there has been dried out seawater, leaving the salts behind. Out west, these are very common. Southeast New Mexico is one place where we take some of our geological engineering majors and we look at some of the deposits there. Last year we looked at some potassium minerals that were being mined near Carlsbad, New Mexico. I grew up in Detroit, and you can see that Michigan is one of the locations where thick salt beds have long been mined. Right under the city of Detroit, they've had a mine for many years, and these evaporite deposits are not uncommon. We get lots of different minerals, not just table salts. We get a lot of fertilizers and other types of minerals from evaporite mineral deposits. One other thing that's important about evaporites is that they're usually fairly close to the surface. That affects the type or influences the type of mining methods that we need in order to extract these. In locations where salt gets deeply buried, something very unusual and unexpected happens. The salt is not that dense. All the layers of material that formed above it is naturally more dense, and as if you took an ice cube and took it to the bottom of a bucket of water, the ice cube wants to rise to the top. Similarly, the salt wants to rise up through the heavier material, and it does. Salt is very malleable, so it will reformulate itself and push its way up through the rock, and that's what happens in a number of locations, creating this type of structure known as a salt dome. And these are very important because they can lead to an accumulation of minerals at the top and also energy resources in places where they form natural oil traps. The same type of deposits that led to the formation of salts at depth also would have deposited biologic materials in some of the beds, which formed the parent material for oil. We'll actually be talking about this a bit more next semester, but the two chapters come together in this structure, and it's one of the more interesting and unusual. We have these in Mississippi, Louisiana, and Texas. These salt dome deposits are an important part of our resources. If you look at evaporite and brine resources in the United States, you can see that we have these in abundance in most places. And if you look at the for each of the different commodities. The middle column shows you the identified resources, and to the right there are undiscovered or hypothetical or speculative resources, and it tells you about how many years, given our current rate of consumption, would continue to be able to take advantage of domestic supplies of these evaporite and brine resources in the United States. Iodine, we only seem to have 100 year of supply of this mineral resource identified, but theoretically we may have about 500 years where we could continue to use iodine as we do. For something like salt, we have currently identified over 1,000 years of resources available to us, and a theoretically unlimited supply of salt because of our ability to extract from the various evaporite deposits that are available to us. When we talk about different mining methods or methods to extract the mineral resources, we can classify these in different ways. Most commonly, we classify them by the type of mining method, where it's located, or what kind of procedures are being used. I should give you a heads up that there are sometimes different names for very similar methods. The two broadest way to classify mining methods are to talk about surface mining methods and underground mining methods. First, looking at surface mining, there are two basic categories: strip mining and open cut, but there are other names for this strip mining, and that might include overburden removal or dragline mining. I've even heard it called mountaintop removal. And there's also open cut mining, which is a little more freeform than mining along a strip of an ore body. The next category is underground mining, and there are lots of different variations, some of which include longwall mining, room and pillar mining, stoping, but there are lots of variations on this, and then if you take stoping to the extreme, it becomes block caving. Let me introduce or show you examples of each of these. In dragline mining, what we use is a great big dragline machine, and it drags a bucket along the overburden or through the ore to collect the large bucket and transfer it to a haul truck for transportation to the processing center. These drag lines are huge, and what it might be difficult to see is that here we see a normal sized vehicle, a car, right next to a drag line to help you get a sense of the scale of this problem. And if you send the drag line to remove the overburden or the stuff you don't want first, you might then have a second pass, and that's what you see going on here in the bottom, where you see the overburden has been removed off the left, and then on the progressing to the right, you'll see the ore has been progressively removed and hauled away for mining and used as a commodity. This dragline mining method is very specific for the types of materials that it works well for. They have to be stratified, and they have to be very close to the surface. These drag lines are very expensive. If you can, you want to buy a used one and reduce your upfront costs, but the dragline mining methods are only useful for shallow units that are laid in layers. So that's really what you need to have in order to make this a viably economic mining method. So not all ore bodies are suitable for this mining method. Does this have impact Earth's surface? Very definitely, and in one of the most intensely obvious ways. Here's some more details on the dragline mining method, where you see the dragline at work on the center, and on the left, and in the upper right you see an example of the haul truck that's about to get a load from the bucket of the dragline, and you see the same size haul truck on the bottom right. You see it over there on the very bottom right, and midair right here you see the bucket of the drag line at work bringing up a load to transfer to the next truck that's going to get in line to take some of the material. So these are a complicated mining method, they are very energy intensive. This dragline is usually drawing a huge amount of electrical energy off the grid and probably resupplying it. When he drops the bucket, he draws when he pulls the bucket, and he gives energy back to the electrical grid when he drops the bucket to try and minimize the total energy use for this mining method. A really good dragline operator gets paid an awful lot of money, and the one thing you can never do if you're on a mine site is interrupt the dragline operator. That person has to stay constantly in action and efficient in their energy use and in their removal of the material. The other type of surface mining method is called open cut or open pit mining, and how you'll see that this is obviously different is we no longer have large strips. We aren't limited to only layered ore bodies. Here you can adapt the orientation and the geometry of the pit in order to adapt to the particular geometry of the ore body. So here you can see some variations where they actually change the orientation of the pit in order to go after the highest grade ore. In this, we no longer have one central drag line removing the material. We have a bunch of excavators working at the active face or in the active layer to get the rock loose, transfer it onto one of the haul trucks, and then the haul truck gradually, slowly drives up the haul road to get the ore up to the surface and for subsequent processing. When we compare different kinds of mining methods, we can see that drag lines are useful for more uniform conditions in layered deposits. This method has more expensive equipment costs. The overburden removal can be inefficient with a significant waste or spoil pile remaining. So in terms of its environmental impact, that's obvious. Open cut or open pit mines also have environmental impacts by certainly, but they are different. Open cut or open pit mines are more inconsistent or variable in shape, and the mining method is more flexible and can be varied for the specific geometry of the ore. The equipment for this method is less expensive, but you still end up with a big hole in the ground or a hole at the surface, and so these have a substantial environmental impact. I've seen people try to use the hole that's left behind for a specific purpose. Sometimes they've been used for surface stormwater drainage. That's about the most successful I've ever seen it. We saw up front one of the earliest examples of one of these open cuts being transformed into a golf course, which is a fairly unusual application of reclaiming the land. But both of these have environmental impacts that will. Now, if we look underground, one of the first methods I'd like to consider is longwall mining. And in this method, we accept that the rock is eventually going to fail, but we try and hold it up at the surface long enough to get it out of the working face and into some haul buckets and have those conveyed up to the surface. So this is an example of longwall mining applied to coal, and as the face advances to the right, you can see that from the left the roof is collapsing behind the active face, and after you remove the hydraulic supports and push them forward as the mining progresses, the roof collapses behind. So here we definitely have failures, and this is a method very common, or not universal, but common in coal mines, but it also used for other kinds of mineral resources. Here's another close-up look at some of the details of longwall mining. We have different kinds of cutters. You might have a toothed cutter up the upper right or a wheeled cutter on the bottom right, grinding away at the material that we're trying to haul out, and then we have conveyor belts that are shown on the left that take the ore away from the working face and haul it up to the surface. While longwall mining might be useful for thin slabs, if you get thicker slabs, or in a very conventional or more traditional mining method, you'd probably have the room and pillar mining method. This is the classic underground mining method, most commonly and most used for the longest time. And one of the advantages of room and pillar mining is that you can mine out the material to leave rooms, leaving enough of the ore in place to create pillars that keep the roof supported. And here you'll see in the bottom of the right hand picture some benching, which can be useful if you have a thick ore so that you might have to take it out in a couple of stages, and you can just leave behind a taller pillar in a case like that. One of the details or features of room and pillar mining is that different parts of the mine will have different activities taking place, and that can be useful so that you can keep a constant working face, even though, and that'll keep ore coming out on a regular basis, even though the actual face that you're drawing the ore from changes from day to day. And you might have blasting in one area of the mine and hauling of ore out in another area, so that the people hauling out ore are far enough away from the blast to keep everything operating smoothly and safely. On the left side of the image here, you'll see some examples of work going on underground in a room and pillar mine. It's very difficult to take photographs in underground, and so you can just see some of the type of equipment that's used and how it has to be adapted for the particular conditions available. No tall trucks in the mine shown there in the bottom left. If you don't have a tabular or slabby ore body, layered ore body, then what you might want to do is use a method that adapts to your ore body, and one of those might be a stoping method. Stoping methods are designed to take out large columns of ore. On the left, you'll see one of these stopes depicted with just a little bit of the rubble left that was after a whole bunch of the ore has been hauled out. We blast the rock to create a collection of rubble that we can bring out on haul trucks, or here you see ore carts along rail lines deep in the below the draw points where the ore is loaded into the uh, the rail cars and taken up to the surface. And underground stoping is adaptable to deeper mining methods or to deeper ore bodies, and if we want to, we can backfill the stope with some of the tailings that we generated at the surface, or waste that we generate at the surface. That can be very useful in getting rid of material after we've extracted the metal that we want. We can take the remaining waste and put it back underground with a bit of cement in it to try and give it strength and fill that stope, that open stope that we removed the ore from. If we don't backfill the stope and we just let the stope actually progress all the way up to the surface, that's actually another mining method, the last one I'll introduce. That's block caving, that's shown here. And here, this is just where the drawing points are used to extract ore all the way until we get a collapse of the rock at the surface and along this chimney that's shown here. This is depicting what's a spiral road, where we are taking the ore from the draw points back up to the surface. So this is a very large scale mine, and this one on the right is a block caving depiction. So those are the various mining methods, and we have to adapt and pick the right mining method for the particular ore body in order to find an economical way of getting out our mineral resources. There is a problem. You might think that underground mining has creates fewer problems at Earth's surface, and that may be true, but it does certainly create some. And one of those, unique to underground mining, is that it can create subsidence or depressions at the surface. In the image on the upper left, you'll see a case that came from Sheridan, Wyoming, where coal mining early in the last century has left depressions that we see at the surface today. In the bottom left, you'll see the beginning of a depression forming above a block caving case in New South Wales, Australia, where they knew that there was going to be subsidence and they had to buy this property even at the surface because they knew they were going to be creating this great big depression at the surface as a result of the deeper mining. One thing on the upper left that I'd like to point out is that there are two different kinds of depressions. One is the pockmarked, darker depressions that you can see, but then there is also these rectangular slabs that came from above a particular room. So they didn't backfill those rooms, and as a result, eventually that void that was created at depth worked its way to become subsidence expressed at the surface. Next, I'd like to turn the attention of our focus to plate tectonics and minerals. Not all, but some mineral deposits are related to plate tectonics. They can often be related to the origin of ore deposits that include iron, gold, copper, and mercury. That's what those symbols refer to. There are a variety of different kinds of plate tectonic processes. If you've had another geology course, these probably have a lot more. You're already aware of some of these, but I'll introduce some here. Is that there are divergent plate boundaries where plates are moving apart, and convergent where plates are coming together and one's moving below another. And at different kinds of boundaries, we get different types of ore deposits. We can often have enrichment of metals at divergent where boundaries where plates are moving apart. Or bodies at divergent boundaries are often related to the movement of ocean waters at those locations. Or deposits at convergent plate boundaries are more commonly related to partial melting of seawater or saturated rock in the oceanic lithosphere getting subducted down to a great depth. There's a lot of danger and oversimplification on this issue. Not all of ore bodies are related to plate boundaries, but some definitely are. I was describing divergent and convergent plate boundaries, and here we have examples of both. We'll see in the center an example of divergent plate boundaries where two plates are being driven apart by an upwelling in the mantle where hot magma deep in Earth's surface is moving up to the surface and causing new crust to be formed at in this case at the East Pacific Rise. And in such a location, it's possible to have metal oxides and sulfides accumulate. If you look at the image on the left or the right, you'll see convergent plate boundaries where one plate is being drawn below another, and the result is that some of the material that had been at Earth's surface is now being taken down to great depth, and that creates the opportunities for particular types of mineral resources to be accumulated. And you'll see examples of different elements shown at the surface and where they might be deposited relative to this convergent plate boundary. Looking at a very specific case of here's a global view of different plates and the types of boundaries that we see. So in the middle of the Atlantic, for example, we'll see a line where two plates are moving apart, or along the Alaskan Aleutian Islands, we'll see a place where one plate is being subducted below another. And in these locations, let's take a look at mercury. Where is mercury found? And one of the things we'll see is that many, but not all, of our mercury ore deposits are located in proximity to one or another type of plate boundary, so that there tends to be agreement between the location of where mercury might be found in economic abundance and where plate boundaries lie. So I did say that there is a connection between these two, but it's not a strict connection. We can see that there are some deposits that are in locations not really connected to the location of an active plate boundary. There are alternatives to mineral resources other than our conventional ones, and one of them that we've been turning to increasingly in recent years, at least to our attention at the research level, is looking for how we might find mineral resources in 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 our oceans. And here's three different types that we'll take a look at. The first one is sulfide deposits. There are massive sulfide deposits containing zinc, copper, iron, and trace amounts of silver that are being produced near what are called black smokers. We'll see pictures of these in a moment. The black smokers occur near oceanic ridges, and they're associated with dark mineral-rich waters that emerge at hot springs and then are circulated in the seawater. The next type of uh, mineral resource we'll talk about here in the oceans is the manganese oxide nodules, and these cover vast parts of deep oceanic floor and can extend up to 50% of can cover up to 50% of the ocean floor in some areas. These nodules, which naturally form and always have been, um, contain about 24% manganese and 14% iron, and also have some copper, nickel, and cobalt. They are most abundant where the sediment is at a minimum, generally at depths of 5 to 7 kilometers, so pretty deep oceanic waters. And the southern Pacific is one area where these are notable for their concentrations. There are also cobalt-enriched manganese crusts present in some locations, and these tend to be near the mid and southwest Pacific, on the flanks of seamounts, and along volcanic ridges and islands. Let's take a look at each of these in a little bit more detail. So at a mid-ocean ridge, we could have a black smoker depicted here that's sending these dark mineral-rich fluids into the ocean and creating circulation of the water that leads to the accumulation of ore deposits nearby that are sulfide rich or sulfur rich and can be used as a resource. Here's another depiction of the black smokers or chimney that show the venting of these hot fluids because of the high pressures. It's not steam at this point, or it's a mixture of water and steam, and we have circulation of this water and the accumulation of massive sulfide deposits. Here's an actual image of one taken from a submarine. The next type of ocean deposit is the manganese nodules, and here's a cross section or a cut through one of these nodules that suggests that they appear to be accumulating through the growth of one ring after another as you get more of this manganese and iron rich nodules forming deep in on the ocean floor. Now let's look at mineral resources and the environmental impact of mining methods. We get environmental impacts from each stage of mining. We get impacts from mineral exploration and testing in the early stages, from the mineral mining itself, from the mineral resource refining or processing methods conducted at the surface, or usually at the surface, and from disposal of the mining waste. The impacts depend on many factors. They depend on the procedures that we use. That's one of the reasons why I introduced the different mining methods, because different kinds of mines will have very different impacts. Also, the hydrologic conditions. A mine in a wet area is going to have impact that's very different than in a mine in a very dry area. There are also climate factors. What's the weathering like? What kind of rock deterioration do you naturally have? That can influence how quickly we get environmental impacts. But we could also have the climate controlling things by such features as what kind of weather we have at the surface in terms of how much runoff to anticipate, the potential for clouds of dust to come from poorly conducted mining procedures. Also, the types of rock and soils that are involved in the mining and the topography. Flatlands versus mountainous areas are going to experience different kinds of environmental problems. In the early stages of mining, during exploration and testing, what are the types of procedures involved and what are the impact? In this stage, we're mapping at the surface what the conditions are. We're conducting geochemical, geophysical, and remote sensing testing to collect data. And we'll also have test drilling. In order to have drilling, that probably means that we had to have roads, which might in itself have a strong impact. If you hadn't had roads in that area to create those roads, you may have had to cut down trees or disturb permafrost, perhaps in Arctic area. And when we drill at the surface, we create a hole into the subsurface, which has some potential for contaminating deeper units, but we could also be bringing up some of the material that we create, that some of the waste that we accumulates at the surface associated with the drilling process. It depends on the drilling process, but we probably will leave some waste behind at the surface, and that certainly has some impact. What are the impacts? They generally tend to be pretty small, but they can be significant in sensitive areas. In an arid environment, if you have wetlands or if you have permafrost, we have some of the examples of lands that may be relatively sensitive even to this stage of mining, which is usually considered generally to be a low impact stage. The next stage would be the extraction and processing. Here we have a direct and obvious impact on the land, the water, the air, and the biological processes. Different kinds of mining methods have different impact. If we're using block caving and creating a big hole, it's obvious. If we're using dragline, we're creating a lot of dust and a big void, and maybe have probably torn down whatever vegetation existed at the surface in our first stage of the mining. This will have indirect impact on the environment beyond the direct ones. We could change the topography. We'll be transporting materials. Something that may have existed only at depth might now be exposed at the surface, and it may have been hundreds of thousands, or if not millions of years since it was at the surface. So we have the potential for indirect impacts in that way. It also is going to have social impacts. If we suddenly have a whole bunch of miners and their families wanting to live in an area that isn't developed to support them, then we're going to have impact. They may not be as carefully regulated as the mining process itself. So this is another what might be seen as an indirect impact of mining, but it's certainly a predictable impact. Let's look in more detail at some of the specific types of impact we have from mining. We'll have land disturbances from getting access to the ore body, from surface mining itself, and even if we use an underground mining method, we are going to have some sort of access point at the surface, and there will be surface impacts. We'll also have a significant accumulation of wastes. It might be, for example, that 40% of a mining area might be used for waste disposal. And in the United States, mining waste constitutes about 40% of all solid waste that's generated in the United States. Special mining methods might be used that are less prone to impacts or might be more prone to impacts depending on the location where they're used. An example of one that has been used that might have reduced impact at the surface might be chemical leaching from gold mining. Is that if we inject chemicals at great depth that act upon the ore to try and dissolve or get the gold to come into the chemicals that we inject, then we can then extract the chemicals and hopefully the gold with it. And if we can get all the chemicals, then it might leave nothing left at depth to create a further impact, and that by using such a method we might reduce our impacts. But it has certain problems with it if you might, for example, not be able to get all the chemical back out. Another very specific problem with environmental problem with mining would be uh, mine acid drainage. This can happen during mining and for decades after mining. Depends on the climate, depends on the ore body, but it may be that rainwater moving through the mine or the mine waste might become acidic and then get out off the mine site and impact a large area or the surrounding region. We can also have water pollution and air pollution, for that matter, from smelting or emissions of sulfur dioxide. And it's also can have significant impact on the biological environment near the mine. If you look at a large mining operation, such as this one near Salt Lake City in Utah, you can see that the mining void, the mine itself, isn't the only problem. We also have piles of waste um, around the mine where we've had the waste material disposed of. And does that affect the topography? Does that create a scar on the surface? Absolutely, undoubtedly. But it's also affecting the drainage of water in the area, which has to be monitored and meet regulatory requirements and the satisfaction of the community that has is potentially impacted by the mine. So when we talk about mining, it goes beyond the mine itself. One of the areas where mining has the opportunity to get off-site is through water pollution. Trace elements leach out of the water that circulates through a mine or through mine waste, and we could have accumulation of cadmium, cobalt, copper, lead, molybdenum, and zinc accumulating in the waters that are transported off-site. Here you have an image on the right showing a depiction of such a transport. You could have problems associated with the flooding of abandoned mines in a wet area. If you create a void at the surface or at depth, it's very likely to accumulate water that can act to leach out these trace elements. If you have the chemistry of the water and the chemistry of the ore in certain combinations, you could have the water becoming acidic with the accumulation of the elements that get into the water, and that can lead to acid mine drainage and acidic and toxic mining wastewater that comes from operations or processing at the surface. Processing of wastes or processing of the ore body material occurs in both surface mines and underground mines. Why that's important is that even if you chose an underground mining method in hopes of reducing impacts at the surface, you probably brought the ore up to the surface and processed it there. That means the waste is up at the surface at some point and has the potential to impact things. In some mining method, you'll remember in stoping, for example, we take some of the waste and take it back underground and use it as backfill to keep the mining process going and try and mine out the stope that's right adjacent to it. But in other mining methods, we leave waste behind at the surface. The waste, it might be in a mucky, muddy water that we send out into a lake. And here, that's what you see on the upper left, where you see sediments accumulating in the shallowest portion of this tailings pond. And in the deeper portion, we probably have some settling of the water, but you need to let that muddy water still to the point that the clays fall out to the bottom, and then clearer water can be released off safely, released off site. On the right, you can see an example of an effort towards reclamation of some of the mined land, where you see some of the waste has been has had grass added to it. It's still susceptible to erosion at that point, and until active forest land develops at that location, there's still susceptibility to further environmental impacts. There's other types of pollution that come from mineral processing, and extraction. One is air pollution. Both the extraction and the processing operations have adverse effects on air quality. Smelting in particular can release enormous quantities of pollutants, and you can have toxic gases accumulating in abandoned mines and coming out during unusual periods where there's a caving event, for example, underground, causing some of the gases that accumulated to be released all at once in an event that could become hazardous to the anyone or anything living in the region. You could also have pollution to the overall biological environment. That's as a result of physical or chemical changes or degradation in the land, soil, or water, or air associated with the mining directly or through indirect um, impact on the biological environment. The roads that are added for a mining process, the operations that take place in the surface might alter which species are going to thrive or die out as a result of that type of disturbance. And that type of damage may take decades or may never permit recovery back to its original conditions. There's also some particular toxicity problems that emerge associated with mining that have historically been tragic in some locations. There's no denying it, and it's one of the things that in modern mining operations, the number of researchers are working hard to avoid these problems. One example that your book points out is the Itai disease in Japan, where chronic and painful bone diseases develop as a result of exposure to zinc, lead, and particularly cadmium had significant impact. When there was accumulation of those minerals in the bones of the victims, they suffered significantly. In gold mining, sometimes and for many years, for decades, mercury has been used to help assist in the extraction of the gold from the ore. But and that's because gold particles can cling to liquid metal, making mercury very useful for trying to get gold out of an ore. But the consequence is mercury, which is very hazardous itself, you wouldn't want to breathe any, is can be released to the environment, and anybody exposed to that is exposed to real environmental risk. Mercury was used back in the 1800s in California, and it's estimated that 4,500 metric tons of mercury was lost to the environment during its use in California during that period. So there are some horrific and particularly dangerous mining procedures that that exist and have existed, and this is just a few of them. There are many others. So what can we do to try and minimize the impact of mining on our environment? We can make sure that there are adequate environmental regulations in place, regulations that forbid bad mining or poor mining practices. We have the Clean Air Act that, if enforced, makes an improvement on our environment. And we can have on and off-site treatment of all waste associated with mining. We can also have knowledge and research development and technology transfer that takes practices that have been developed, that have been created in developed countries, and transfer that knowledge base to developing countries. Regulations as well, if they are implemented in developing countries, can improve the safety for the workers there and the total reduction on the impact on Earth's environment. As for land reclamation, currently about 50% of land used in the United States is reclaimed. So that, you can say, is a mark of how good things are or how poor things are, depending upon your perspective. But the reality is that the impact on Earth's surface is undeniable, and even reclaimed land has different degrees to which it might be perceived as useful or returned to its original state, or the extent to which it's returned to its original state. Increasingly, we have opportunities for the use of new biotechnology in mining that goes some way and offers some hope for reducing some impacts. And I think more fundamentally, we can practice the 3 R's of waste management. Everybody taking responsibility that mining problems are something we all contribute to. And by practicing the 3 R's, which are reduce, reuse, recycle, we can do our own individual parts to begin the process of reducing the impact of mining on our environment. This image shows you an example of some of the impacts and how they can definitely get off site. In the back you can see some of the smokestacks from a smelting operation, and you can see that the environment, not even immediately adjacent to the smelting, is impacted, and the air pollution from North Dakota and South Dakota is known to get all the way to the East Coast quite easily. So the impact of mining is not local. Although it's local, it goes beyond just the local environment. Why should we recycle? Well, consider the impact on wastes itself. Mining wastes are often toxic to humans. They can damage the natural ecosystem. They can degrade the air, the water, and the soil in the area and the region. If we use land for disposal of the waste, then the land that we're using to put the waste on is also affected. And for many of us, the mine wastes are regarded as aesthetically undesirable. Beyond just the aesthetics of the mine waste, we also have to consider what's lost when the mine is created. If there was a forest or a community that was in place before a mine went in, that's gone. So it's more than just the aesthetics, it's the social structure that may be gone, or it's a natural resource that may be gone by the introduction of mining into a region. This is a depiction of how recycling can help reduce the impact on the earth. When we have disposal of a waste or exploration and resource extraction, we're directly impacting the earth. The resources that we extract have to go through a refining process to get the metals that or basic ingredients that are useful in products. But if we can recycle those products, we can help reduce the involving the earth in the generation of that basic commodity that our society is seeking. When we recycle, we probably have our most important reduction or impact on the potential harm of mining to our environment. Waste itself contains recyclable materials. If we haven't sorted our waste and if we haven't made adequate efforts at extracting the recyclable materials. If we recycle instead of generate new commodities from ore, we'll save energy, money, land, mineral resources, and avoid having to introduce more mines. We save significant energy and cost when we recycle instead of refining ore materials. It takes an awful lot of energy to crush up an ore to extract the mineral that often the metal that we're after. Even in coal, we have to process the material. You can't take coal directly out of the ground without processing it. Usually we have to wash it and get rid of fines that aren't going to burn in a coal process. So there's a lot of energy that goes into that process of getting the commodity ready for use. Recycling has been proved as it's been proven to be profitable and a workable alternative to mining to get new mineral resources. Let's talk more about that. When it comes to recycling, we have to recognize some of the inherent advantages. It takes about one third as much energy to produce steel from recycled scrap compared to from original iron ore. So that's actually for an ore that's already typically pretty rich in the commodity we're after. For other metals, it could be even more of an energy saving. In 2006, the total recycled steel in the United States was about 18.5 billion, making iron and steel about 50% of our needs for that commodity were met through recycling. In other years, that's been up to 90%. We've had some fluctuations in the economy recently that's caused commodity prices to vary, which have led scrap centers to set some of the resources aside until the commodity price rose again to support the increased use of recycled materials. While for iron and steel, it's been about 50 to 90% in recent years. For other commodities, for lead, for example, it's been about 73% of our needs have been met through recycling. For aluminum, about 43%. We all have to recycle our aluminum pop cans. And for copper, it's about 32% of our needs being met through recycling. For nickel, 43%, and for titanium, 47%. Mining and sustainability. What is sustainability? It's in general, it's not, it's thinking about more than today. It's developing a long-term strategy for consuming what resources we have and what resources we need. We can also try and find alternatives for metals or other materials that we need. One example would be using glass fiber cable instead of copper wires, which by changing what materials we used, we've changed what kind of mineral mining impacts we're going to have. Our government or governments could negotiate more wisely with other governments for a sharing of commodities and not just sending the environmental problems to another country. Our governments could adopt laws to support environmental sustainability or not. Or our governments could support a dialogue between industry and environmental advocates to support both growth and sustainability. Such a wise discussions seeking solutions to problems doesn't always happen. Another thing that we can work on for achieving sustainability would be more research and development on innovative solutions or ways to use mineral products more efficiently or to mine more efficiently with reduced impact on our environment. Thank you for your attention. See you next week.